So, welcome back, Calculus. We're here in part 2 of AB 15, which is function analysis, if you didn't know what we were doing. So, we're establishing some vocabulary here. Critical values, this is where the slope is equal to 0 or where the function is not differentiable. So, either f prime of x equals 0 or f prime of x is undefined, which usually is something like a number over 0 kind of thing. Visually is where there's a horizontal tangent line or a vertical tangent line. That's kind of what we're going for. And then stationary points is really just a horizontal tangent line. So that's kind of a vocabulary word we're going to be employing here. Relative mins, in other words, that's when we're going down and then up. This is the bottom of the hill, the bottom of where things kind of, they change from decreasing before. Let's color code that for us. Decreasing before and then increasing after. So we hit a minimum. Relative max is actually the exact opposite. It's, we're going up and then we hit a maximum and then we come back down. What goes up must come down. So we're positive before and then negative after, then we hit a maximum. Relative extreme is just kind of grouping both of those things into the same idea. This whole idea of absolute, we're going to get into that later. That's a big deal in an entire section and unit that we look at after this. But when we're talking about relative mins and maxes, the idea to consider is that you can have a graph that looks like this, and then down, and then up again, and then down again. And this is kind of where it gets even more interesting, that this, what are we trying to do? Oh no, that's not what I was trying to do. Here we go. This minimum, the second minimum here, is higher than this maximum. And we have two maximums and two minimums. So what you need to consider is that relative just means in that general area. Not in the entire graph, but just in that general area. Do we have a bump up or a bump down? Those kind of things. Now the last thing, inflection points, or absolutes are kind of like the highest and the lowest points. Highest and lowest, and that's just kind of in general what we're looking at. But we're going to get into those way more in depth later. So we're not going to really discuss them a whole lot right now. The x value where the curve switches concavity, so the x value where the curve switches concavity is called an inflection point. And that's going to happen when we change from concave down to concave up. Or, it could even be more simply looking like this. And this is kind of not as obvious. It's like half a smiley face and half a sad face. But that's still concave down and still concave up. And this is where the second derivative equals 0 or fails to exist. So we're looking at when the second derivative equals 0 or where the second derivative does not exist. So let's use this information. First, we're looking at these pieces in the pictures, and we're going to determine whether they're a critical point, relative min, relative max, stationary point, or inflection point. So the first one, right here, critical point. Does it equal 0? Yes. And in fact, we're going to go ahead and get this out of the way. These are all different types of critical points. Critical values, critical points. But let's look at them more in depth and see exactly what kind of critical values they are. So the first one, A, is it a relative min? No. But it is a relative max, that's true. Is it stationary point? In other words, is it flat, horizontal? Yeah, it is. Is it an inflection point? No, it's not, because it's sad the whole time. It's sad before it, sad after it. It doesn't change its happiness or sadness. So B, is that a relative min? Yes, it is. It's not a max. You can't be both a max and a min. kind of another way to check yourself there. Is it stationary? Yes, it is. It's not an inflection point for the same reasons as A. Because we go down, we come up, and we're the same concavity throughout. So now let's look at C. So C here, we are flat. That's true. So it is going to be a stationary point. Is it a relative min? No, because we don't go back up. We're negative and then negative again. We're decreasing and decreasing again. So that means that we're actually an inflection point. We are stationary, but we're an inflection point. And D is the same thing. It flattens out and it's an inflection point. So we flatten out, but now we're positive and positive slope. We're going up the whole time. But we change concavity here because this one is concave down for part D on the left. But on the right is concave up. Let's look at E, F, G, and H. Now these are different because there's no flat slopes on each of these. In fact, this is more first derivative does not exist. It's not differentiable at that point. But it still represents something critical and something interesting happening right here at E. We do hit a high point, so we are going to call that a relative maximum. And for F, it's kind of the same idea. It's not stationary, it's not an inflection point. And for F, it's the same idea that we hit a relative minimum. But now, let's talk about the concavity of these. In fact, both of these are concave up the entire time. Or actually, no, concavity for the second one, concavity equals zero. No concavity. Why? Because it's a straight line. There's no bend. For these ones, there's bend, but we're concave up on one side, concave up on the other side as well. Now for G and H, we actually go vertical. So this is F prime of X does not exist as well. But this one, instead of coming back down, it still goes up. And when we go vertical like that, and then change direction, this changes concavity because we're concave up before and concave up after. And for this part H here, we're concave down and then concave up. So we change concavity. So it's not a relative min, not a relative max, it's not stationary, but both of those are definitely inflection points. Now let's apply this understanding into actual graphs. So right now, when I'm looking at f prime of x, I'm looking at, is it positive above the y-axis or is it negative below the y-axis? Because that's going to translate into a function over here. And in fact, this one's positive. It's a positive slope. Positive slope. So f prime of x is equal to 2, which is greater than 0. So it's a positive slope. So I just need to have a slope that equals 2. So I'm going to go over 1 up 2, over 1 up 2. And the idea here is that this straight line is only one possible f of x. Why? Because f of x could equal 2x. It could equal 2x plus 1. It could equal 2x minus 1. It could equal 2x plus 1,000. But each of these constants here, if we were to take the derivative, they would disappear. So those constants kind of allow us to shift this graph up or down. We're not really concerned about location at this point. We're just concerned about slope. So let's look at the next one. Our slope starts out negative down here. We are below the graph on this point. Oh, by the way, you need colored pencils. I'm using red and blue here. You should probably do the same. You should color these lines. So over here, I'm negative. And on the other side, I'm positive. And not just positive, but getting more and more positive. So this is positive slope, and this is negative slope. So that means this graph is going to be 0 in the middle too. 0 right here in the middle. So that means I have a critical value or a critical point at x equals 0. So at x equals 0, we're going to have a flat line. And to the left, before x equals 0, we're going to be negative. And after x equals 0, we're going to be positive. Does this make sense algebraically? I mean, look at this graph. This kind of looks like x squared. Maybe x squared over 2 or something, but it's just x squared, some type of x squared. What would the derivative be? That'd be something like 2x, or a linear equation. This is a quadratic. That totally makes sense. We take the derivative of a quadratic equation, we should get a linear equation. And that's the relationship we're looking at. Let's do some more of these. Okay, so now I'm going to look for my critical value. Let's start with that. We have a critical value here at 0. So this is f prime of x equals 0. So that means at 0 I'm going to have a flat slope. Now I could put this flat slope anywhere I want on this axis as long as x equals 0. Let's use this one. It doesn't really matter where we start, up or down, but it does matter that it's at x equals 0. And before, whoops, jump back here. Before x, we are a negative slope. Why? Because we're below the x-axis. And after 0, x equals 0, we are also a negative slope. So that means we have to go a negative slope and then another negative slope. But in between, we flatten out. So how do we do that? We start out negative, and then we're going to get flat. So we come here and we get flat. And then we start from flat, and then we turn more negative. So that would be our function there. And this, again, makes sense. Why? Well, this graph over here, this looks like something kind of, it's approximately negative x cubed, because positive x cubed would have looked like that, increasing all the time. And what's the derivative of negative x cubed? It's, approximately over here, negative 3x squared, which this kind of looks like too. Now, these constants, this constant here, this negative 3 and this negative 1, whether it's that way or not, those aren't exact. And that's why we're kind of looking at approximating this visually. But the slopes should be near on point. Let's look at this next one. So if I look at this line, I see that I have a critical value this time at x equals 1. X equals 1 is flat. So that means at 1 we're going to be flat. And before 1, we have f prime of x is less than 0. It's negative over here. After 1, again, f prime of x is less than 0. Still negative. So again, we kind of have that same idea. This is a little more constant rate of change here. We have this, it's pretty pointy, but the slight difference is that our flat spot is at 1, not at 0. But we still have a similar idea to what we had before, where we were negative, but then we flatten out. So we were negative here before 1, then we flatten out at 1. And then we go from flat, and we get more negative again. Remember, slow the video down when you need to, but we're going to keep moving here. Let's look at the next one. Ooh, now we got some more action. Look at all this stuff going on. Let's start with our critical values. We're going to have critical values here at, if I can use the pen, here at x equals negative 4, x equals negative 1, and x equals 4. Well, let's start with just one of them. How about at negative 4 will be flat. Before negative 4, we have f prime is less than 0. The slope is negative. So we're going to be negative and then flatten out here. Between negative 4 and negative 1, now we're going to be positive. F prime is positive here. That's all above 0. So that means we're going to increase. Until we get to -1, then we flatten out again. So we're going to be positive. And then at -1, we're going to start to flatten out a little bit. And then the next piece here, now we're going to go back to negative. Down here below the x-axis, this is a negative value for f prime is less than 0 again. So now we're going to be a decreasing slope until we get to 4. So we're going to decrease, decrease, decrease. And then at 4, we start to flatten out again. So we're going to be flat here at 4. Then after 4, what happens? Well, we go back positive. So right here, f prime is greater than 0 again. So now we go back to increasing. So notice the relationship here. When f prime is above the x-axis, f of x, the original function, is going to be positive or increasing slope. Similarly, when f prime is less than 0 or below the x-axis, the original function has a decreasing slope. Okay, let's do another one. Here, f prime of x is at 0 and 0. So those are our critical points at x equals -4 and x equals 1. So we're going to start with a, let's do one here below the x-axis just to mix it up a little bit. What are we before -4? That's going to be a negative value there. So right here, f prime is less than 0. That means we're going to be decreasing in the original function. So we go down to it, but then we flatten out at -4. And then between -4 and 1, we are positive. We're increasing again. So now we're going to increase. Increase until we get to 1. And we flatten out at 1. And then after 1, this is interesting. Here's something different. You know, we go back positive again. So now it's, again, f prime is greater than, not less than, greater than 0. We're positive again. So now we're going to increase again. We're going to go back up. Kind of cool. And that's actually a point of inflection there, because we changed concavity. All right. Let's look at this again. Okay, so now we got some curves going on in our derivatives, but we still do the same kind of analysis. We look for our critical value, so we know at 0 we're going to be flat. You know, let's put this one right on 0. Doesn't need to be different. And before 0, we start out, you know, with like a slope of -4, and then we eventually flatten out to a slope of 0 here. So this is negative, which means we're going to be decreasing. We start out with a slope of -4 around here, and then we start to flatten out. And then after that, now notice how this one took a little bit longer to flatten out. That means on the other side, when we're an increasing slope, a positive slope, it's going to go up a little bit faster. So it's going to have a faster curvature to it on the right side. It's going to go up really fast. There we go. So this is positive. That side was negative. That's why the slope is positive or increasing, and then on the left side the slope was negative. That's kind of almost a digression. It's like it got simpler. Let's look at the next one here. Okay, now we got some mixing it up again. We're going to start out with our critical values. We have a critical value here at -4. We also have a critical value here at 3. And this interesting sharp turn, maybe we can interpret that in the graph too. So the first thing is we start out negative, up till -4. So we're going to come down to -4 and and then flatten out. Oops, I wanted purple for that. That's okay. There we go, fixed it. Now we're going to be positive after that. Then we make an abrupt change and start slowing down again. So it's going to be interesting to see how that plays out. So we're going to go positive. We're slowly increasing, but then we flatten out really fast once we get to 3. Oh, we need more space in this. I increased too fast here. Let's redo this. So we're slowly increasing, but then at 1, we kind of change that. Now we're slowing down. There we go. And at 3, we hit a flat spot. And then after 3, now we're back to negative again, but we're on the bottom. So after 3, now we're going to be decreasing. All right, so we're seeing a lot of this interesting stuff kind of take place visually. Do we have any more? I think we do. And is this the last one? Let's go ahead and let's see. How many do we have? So we got 2 more visuals. We're going to do these last 2 visuals and we'll stop there. And we'll do the last one, which is more algebraic in part 3. Okay, you are given a graph f prime of x, draw a picture of f of x, same kind of thing we've been doing this whole time. So now we got this graph. We start out kind of pretty constant slope here, and then all of a sudden we just drop down, bam, to 0. And then same kind of thing, we hit 0, and then we start out kind of slow, and we kind of hit a slope, and then we flatten out a little bit. So we're negative after, but positive before. So where does all that change? It changes here at x equals negative 1. So that's where our flat spot's going to be. But before that, we have positive slopes. So that means we're actually coming from below it, down here. So we've got pretty constant slope going, and then all of a sudden we start slowing down. Then on the right side, we start to speed up, but then we kind of reach a constant slope and then kind of stick to that. Oops, let's take that last curve piece out there. That looks a little better. Now, does it matter that you had to reach these constant values here? Not necessarily, but it's just kind of interesting to see how that works. Whoa, I did something weird. He's like, Mr. Butler, you did that wrong. Yes, I did, because it should have been decreasing. Should have been decreasing. Decreasing slope means I'm going down, not back up, going down. There we go. So negative slope. Now we got really interesting stuff. Lots of action. So we got a critical value here, a critical value at 2, and a critical value at 2.5. And before 1.5, we're positive, because we're above the x-axis. But then between 1.5 and 2, just for that little half domain there in x, we're negative. And then between 2 and 2.5, we're still negative. But we went to negative infinity slope, you could say. And then above the axis here at the end, we're back to positive. So this is an interesting graph to look at. Let's see what would happen. So we're going to start out positive. So we're increasing slope until we get to 1.5. So increasing slope until we get to 1.5, and then we're going to flatten out right there. And then just for a half section, we're decreasing. And we're not only decreasing, but we're decreasing down to vertical. That's like a negative infinity slope. Really, really negative number, not negative 8. I was thinking negative infinity. I shouldn't even say that. But then at 2, we're starting from this vertical negative infinity slope and then slowly getting back to 0 at 3. Is that what it is? At 3, right? this tail off. No, at 2.5. 2.5. Can't even see what we're doing here. All right. So from 2 to 2.5, we are negative. But then at 2.5, we flatten out. Then after 2.5, between 2.5 and after that, completely, then we go back up. We're increasing again. So what's this interesting relationship that's happening here with this f prime of x went vertical? That means that the second derivative, you could say, does not exist. And what happens when the second derivative does not exist? That means, most likely, a point of inflection, because we're changing stuff there. We're changing concavity, and that's right here. So at this point, x equals 2, it's right here, where we were concave down before, but then concave up after. Interesting stuff. Let's look at the next one. Now we got, again, this kind of idea where we're going to see points of inflection take place. Because before our critical value, we're positive, and after our critical value, we're positive, and in between, we hit this 0. Well, let's see what happens. That means that I'm going to increase until x equals 0. But at x equals 0, I'll hit a 0 slope. So I flatten out at 0. But then I just jump back up again, and I'm increasing again. So that's kind of interesting there too. We have a point of inflection. And this last one, this is probably one of the most interesting of the day. We have a positive slope here. Okay, remember, we are above the x-axis, therefore we're positive. Slope is positive. Even though you want to say slope is negative because this line looks like it's going down. We're just looking at above or below. Now we're below the x-axis, so we're negative. And then all of a sudden we just jump back to positive. No 0 in between. We're going to skip over it. We're going to skip over this to get over to the positive values. And then after x equals about 4.5, then we get back to negative down here with a critical value at about 4.5 and a critical value at 0. So let's start with 1 at 0. Now here's a flat line at x equals 0. And we're going to be positive before and negative after. So we're positive before and then negative after, but only until about 1. And then at 1, something interesting happens. We were a negative slope, but then all of a sudden we changed to positive slope. No, warning or anything. We're just positive. And then after that, after we are positive slope, we start to flatten out, and we are going to flatten here at x equals 4.5. That's where we're going. At 4.5, then we get really flat. So right about there. Then what happens after 4.5? Back down to negative again. So what's key in this one that kind of stands out? It's this point right here. It's an abrupt change from negative to positive. That means that we're changing abruptly from negative to positive and no flat, no 0 in between. No slope that's flat. No slope 0 in between. No smoothness. That means we're sharp. Sharp turns. All right. So, is that it? Is there one more? I think that's it. Yeah, so from here on out, this is going to be part 3. We're going to go and stop this part of the video here. That way you guys can kind of chunk it and Do it in pieces instead of trying to do this all at once. Take a break, you know. This is like intermission. See you later.